Ladies and gentlemen, welcome back to lesson 14 in group theory. In this lesson, we'll be talking about the quotient group. What is the quotient group? Well, imagine you have a group G. You'd like to study not this group, but something that is a bit coarser than this group. Imagine you have grains of sand. You don't want to work with each individual grain. You'd like to clump up these grains together to form bigger rocks. So what we're doing here essentially is taking a high resolution group and making it into lower resolution so we can better understand its structure. Take this drawing on the right, for example. You have a high resolution group G given by the rectangle over there. And what I'm doing here is I'm taking each high resolution pixel and I'm compressing it all into one representative pixel. So what I'm doing is I'm losing information, but information that I don't really want to serve my purposes in a smaller group H. So this is what I would call the cosets, each representing a set of elements in the group. So this is what I will be defining first. What is a coset? What are examples of cosets in groups that we've already discussed? And afterwards, I will show you that cosets will give an exact partition of a group. And lastly, we will go into what a normal subgroup is, what a quotient group is, and how do these two relate. Let's get started. Let us start with the definition of a coset. If G is a group, let G be some element in G, and H a subgroup of G. The sets denoted by G times H is equal to all the elements H in H when they are multiplied by G. So essentially we're taking this element G and we're multiplying by all of the elements in H, yielding us this coset GH. This coset is a left coset since the multiplication is done on the left by G. A right coset similarly is denoted by H times G, which is the multiplication from the right by G. Let us look at a basic and intuitive example of cosets. If G is the additive group of integers, we take the subgroup H to be the multiples of 3, which we denote by 3z, or the subgroup generated by 3. So essentially, it is all the multiples of 3 in the integers, minus 3, 0, 3, and so on. So now it's time to know what are the left cosets that are possible for 3z. So to get a left coset, we need to get an element G in the group, and we need to operate it on the subgroup H. And this element, we can take it to be the identity element 0, for example, and we will add then 0 to all of the elements. Remember, the operation here is addition. So GH, in our definition, would be G plus H because of the operation that we're taking. So we would add 0 to all of the elements in 3z. So 0 plus minus 3, 0 plus 0, and 0 plus 3. But that just gives us the same set again, minus 3, 0, 3, which is 3z. So you can see that the coset 0 plus 3z is none other than 3z itself. The next coset that we can take is by adding the element 1 to 3z. We would have 1 plus all of the elements that lie in H, and that would give us minus 2, 1, and 4. So this is another left coset of 3z. Another left coset would be by adding 2 to all of the elements in 3z, which gives 2, 2, 2 plus all of the elements, giving us minus 1, minus 1, 2, and 5. Now you might ask, is there an infinite number of cosets? Can we just keep adding numbers and we get a different coset each time? The answer is no, and here I'll show you why. If we add 3 to this coset, we will get 3, 3, and 3, plus all the elements in 3z, giving us 0, 3, and 6. But that is just 3z. That is just equal to 0 plus 3z. So you can see that we're getting into a cycle of repetition here. We're not going to get infinite number of cosets, even though 3z is infinite and z, of course, is infinite. The number of cosets is finite in this case. Of course, that does not mean there is always a finite number of cosets given an infinite group, but in our example here, we obtained a finite number, which is just 3 cosets. We can label them by 0 plus 3z, or 3 plus 3z, or even minus 6 plus 3z. You can guess that it could be any multiple of 3 in this case. And in the next coset, we could have 1 plus 3z, or 4 plus 3z, or minus 2 plus 3z, etc. The third coset can be 2 plus 3z, or 5 plus 3z, or minus 1 plus 3z, etc. So even though the representations here, the representatives, are different, they all represent the same coset, which is 0 plus 3z. So we might as well choose one of those elements to represent, and we can choose 0 in this case. Same here, we can choose 1 and we can choose 2. So in the end, there are only 3 left cosets of 3z. Why left? Because the addition of the elements is done on 3z from the left. Now that we have done the addition from the left, if we did it from the right, it would yield us the same result. It would give us 0 plus 3z, which is equal to 3z plus 0, because it's the same set. It does not matter where we add from, because addition is a commutative operation. So we notice that a plus 3z is equal to 3z plus a for any integer a. Simply because addition is abelian, so whether we have left cosets or right cosets, the results are the same. So all the left cosets with a are equal to their respective right cosets with a. 0 plus 3z is equal to 3z plus 0. 1 plus 3z is equal to 3z plus 1. 2 plus 3z is 3z plus 2. All the left cosets equal the right cosets. This property, where left and right cosets are equal, will be very important later on in the lesson. In the next example, we will take the dihedral group D8. We consider H to be the subgroup generated by R, the rotations, which we can denote by this, and we will take the left cosets of H. So to take the left cosets, we need to consider the elements in D8, and we then multiply these elements by the entire subgroup H. The first set of elements we'll take is r to the k for any integer k. So r to the k times h will be the composition of r to the k with each individual element in h. So we get the resulting set r to the k times r, giving us r to the k plus 1. Similarly, r to the k plus 2 and r to the k plus 3. So note that all of these elements are distinct, none of which is equal to any other element in this set. And also note that each of these elements is a multiple of r, so they all have to lie in H. So in conclusion, this element has to be one of those elements here, and this element has to be another element over there. So this set equals, at the end of the day, to 1r, r squared, and r cubed. But that is exactly equal to h. So we conclude that the left coset rkh is equal to exactly h. Now let us see what sh looks like as a coset. So we multiply all of the elements of H by S, and we get S, SR, SR square, and SR cube. So this is what we obtain here. Now, what about the elements of the form SR to the K times H? Well, we can use associativity here to say this is equal to S times R to the K times H. But we know that R to the K times H is equal to H, and this is equal to SH. Thus, we have found out what all of the cosets of H look like, because all of the elements in the 8 have either the form R to the K, S, or SR to the K. So now that we have done multiplication of the elements of the group by H from the left, we have obtained the left cosets. It is time to find out what the right cosets of H look like. So we will do the same kind of thing, but instead of doing mindless computation, just notice that if you multiply R to the K by the elements of H, you will obtain the same result because of the exponent laws. So you have R to the K times R to the L is equal to R to the K plus L is equal to R to the L plus K is equal to R to the L, R to the K. So it does not matter the order in which we multiply our powers of R. So we have that naturally H times R to the K is equal to R to the K times H. The right cosets and left cosets are equal for this particular R to the K coset. And what about HS? Okay, HS, what does it look like? So we multiply the elements of H by S from the right. So it's going to be S times RS times R square S times R cube S. But we know from properties that we've seen in dihedral groups that we can switch the order in which we multiply R and S, provided that we revert the sign of R. So this equals to S, SR minus 1, SR minus 2, and SR minus 3. And now we can use another property of dealing with these things to say that this is equal to S, SR, okay, minus 1 plus 4 is 3, minus 2 plus 4 is 2, and minus 3 plus 4 is 1. So at the end of the day, we obtain the exact same set here, just that the elements are put in a different order, but in set theory, it does not matter. These two sets are equal. So we find out again that left and right coset is equal. So for R to the K and for S, we have equality. And no doubt, if we have equality on these both, and since SR to the K H is equal to SH, then we have the same result for SR to the K H. So this means that H times SR to the K is equal to SR to the K H. So for this particular choice of H, notice that all of the left cosets are equal to their respective right cosets. Again, keep this in mind when we move on throughout the lesson. This will be important. To highlight this property of left coset being equal to right coset, I'd like to give another example for H such that this is not the case. So if H is the subgroup generated by S, which is the reflection, we will take the left coset of H. We will take it with a particular element, which is just R. So R times H would simply be R multiplied by all of the elements in H. So it's R and RS. And similarly, HR would be the multiplication from the right by R, which is R and SR. Okay, but note that RS and SR are not equal. In fact, RS is equal to SR to the power minus 1, and that is not equal to SR unless n is equal to 1, which is not the case here. So Since RH and HR are not equal, we have that the left coset is not equal to the right coset. So there are some choices of H for which we have equality for no matter what coset, and there are other cases of H for which that is not the case. This will be able to prove something important later on. Let us now talk about coset partitions. To get involved in this topic, you need to have some background knowledge on equivalence relations. This is something that you might have taken or you will take in discrete mathematics. But I will give you a brief summary of what an equivalence relation is. So an equivalence relation is a relation between two elements such that it satisfies certain nice properties. The most basic example of an equivalence relation is the equality of two elements. So the equality of the two elements has three nice properties, which are A is equal to A. That is what we call a reflexive property. And if A equals B, then B equals A. That is the symmetric property. And lastly, we have the transitive property. If A equals B and B equals C, then A is equal to C. So these three properties define an equivalence relation. And the nice thing is, an equivalence relation partitions the set into partitions. A partition is what? Imagine the set as what I'm drawing here. The equivalence relation will just divide up this set into pieces like that. And the cool thing here is that these pieces are disjoint. They don't really intersect one another. So if an element is inside one of those pieces, it is definitely not inside another piece at the same time. So the intersection of all of these pieces is empty. So the relation here, A equals A, for example, we have that 3 is over here, and 6 minus 3 is over here as well. But 2, because 2 is not equal to 3, it is in another partition in the set of integers, let's say. So we would have 1, but also 5 minus 4 is over there as well, and maybe 2 over 2. So all of these elements are inside this partition. And all of these elements are inside that partition. So you can see that equivalence relations, they divide up the set into nice pieces that don't intersect with each other. So this thing can be done more generally, not necessarily just for equality. We can do it for any equivalence relation that satisfies these three properties. And this is what we will be defining now. If G is a group and H a subgroup of G, we can define an equivalence relation as follows. For two elements A and B in G, we have that the equivalence relation A and B is such that B is an element of the coset AH. So it is an if and only if statement. A is equivalent to B if and only if B is in the coset of A. We can do a bit of algebra here, A to the inverse in the both sides, to see that we can cancel out the A on the right-hand side, and we find out that A inverse times B is an element in H. So once we have this relation or this relation, we can say that A and B are in the same equivalence class. And this is an equivalence relation. So in this case, the left coset AH is an equivalence class which we denote by A bar. And this is the set of all the B in G such that B is inside the coset AH. So for example, in the integers Z, we had H is equal to 3Z. The left coset, we had 0. we can say it's 0 plus 3z or 0 bar. So 0 bar is all of the integers b and z such that b is inside ah being 0 plus 3z. But we know that the integers in 0 plus 3z are just the multiples of 3, so we can just say this is equal to the multiples of 3. 3k for k integers. So we can have 0 bar, we can have 1 bar, 2 bar. Notice that 3 bar is equal to 0 bar. And for example, minus 1 bar is equal to 2 bar. So following the same argument about partitioning the set into nice partitions that don't intersect each other, we conclude that because of this equivalence relation that we defined, we can say left cosets are the equivalence classes of this relation. So in other words, if we have the group G, so then we can partition the group G into left cosets. So this would be, for example, 0 bar, this would be 1 bar, and this would be 2 bar. Well, yeah, just like that. 0 bar, 1 bar, and 2 bar, and Z, when you take H is equal to 3Z. Of course, if you take another H, this would be partitioned in a different way. If H, for example, was 4Z, then we would partition it into 0 bar, 1 bar, 2 bar, and 3 bar. So we would add another partition here. We would call it 3 bar. So it would just partition everything in a different way. But the point is, for each fixed choice of H, the subgroup, we would have a certain partition of the group according to the left cosets. The same could be said about right cosets. So left cosets could make a partition and right cosets could make another partition with their own equivalence relation where A is equivalent to B if and only if B is an element of the right coset HA. So it's important to distinguish between left and right cosets because not always it is the case that we have commutativity as we've seen in the example here. So we don't always have the same sort of partition if we go from the left or from the right. However, the results for the individual side, whether we take left or right, are the same. So from here on out, we will work only with left cosets, unless otherwise specified, referring to them as just cosets, and the same results will apply to the right cosets in an analogous fashion. Immediately after defining the equivalence relation on left cosets and getting the equivalence classes, we will work on stating this proposition, but the proof of this proposition will be done in the next video, so stay tuned for that. Let G be a group, H a subgroup of G. The first result of the proposition states that if we have two elements in G and we look at their left cosets, then either AH is equal to BH or their intersection is empty. So either they're the same coset or they do not intersect at all, making them a partition, a proper partition of the group G. The second result talks about every element G in G, where does it belong? So every element G in G, not only does it belong to one of the cosets of H, but it only belongs to that coset. It does not belong to any other coset of H. So for example, if G was here, then we can never have that G is here as well, unless of course AH is equal to CH. The third result says that there is a bijection, a bijective map between H and GH. A bijective map is one where it is both injective and surjective. And in particular, we have that the cardinality of the sets H and GH are equal. And this is a very important result we will be using in lesson 15, where we talk about Lagrange's theorem, one of the most important theorems in group theory, and frankly, the turning point of this series. Now that we have defined a coset, and we've seen examples of cosets, we've seen that cosets partition the set or the group G into partitions, then we can now get into what is a quotient group is and what a normal subgroup is. So remember our example in the integers and 3z, we had the cosets 0 bar, 1 bar, and 2 bar. Remember that 3 bar is equal to 0 bar, so there would only be repetition, and it suffices just to include these 3 cosets, which is all of the cosets that they are for 3z. So if we take the set of these 3 cosets, this is the topic of the definition that I'm about to tell you here. If G is a group, H a subgroup of G, then the set of cosets of H, which is denoted by G/H, GH, is equal to just the set of cosets of H, basically. So here, we're taking the cosets of H as G goes through the entire group. So the set of cosets Z, 3Z, is equal to 0 bar, 1 bar, 2 bar. 3 bar, 4 bar, 5 bar, all of these others are equal to one of those 3 elements. Therefore, this set is a finite set. So this is my group G, and this is my 3ZH. But hey, we've seen this notation before, Z, 3Z. This is the cyclic group of 3 elements. This is the elements modulo 3. What is going on? Well, it turns out that we take the elements modulo 3, we're essentially ignoring all of the information on the integers except whether they are divisible by 3 or not. So if they're divisible by 3, they are in the coset 0 bar. That means there are a multiple of 3 here. If they are not divisible by 3, but it's in the form 3k plus 1, then it's going to be in 1 bar. And if it's 3k plus 2, then it's going to be in the coset 2 bar. So we've taken the cosets and we've taken the set of the cosets. So essentially, this is the set containing the multiples of 3, the multiples of 3 plus 1, and the multiples of 3 plus 2. And that forms our GH, our Z3Z for this example. So think back to the analogy of making the fine grains of sand into coarser grains of rocks. This is exactly what I'm talking about here. If we think about GH as the image of psi, psi is basically the surjective map that takes the element G and gives the coset GH. It is essentially taking these fine grains of sand, putting them all into clumps of rock. And the image, what results, is the GH. Now, it would be a shame if we did all of this work and then GH is not a group. We would like GH to have a structure the same way that G has a structure as a group. And so the question arises, can GH be a group? If so, what is its group operation? What is the identity? And what is the inverse of a coset of H, an element in GH? The answer is yes, it can be a group, but only if H is a normal subgroup of G. And that is the importance of having a normal subgroup, is because then and only then GH is a group. And I will be defining what a normal subgroup is. You will now find that the definition of a normal subgroup is not that strange to us. In fact, we've already seen examples of subgroups that are normal and those which are not. I just haven't told you yet that they were normal. In the definition, a subgroup H of G is normal if for all G in G, the left coset is equal to the right coset. In this case, we write H is a normal subgroup of G. Can you now remember the example where we said that if H in the group, the dihedral group D8, if H is generated by the rotation, then we have that for all of the elements in D8, the left and right cosets are equal. So H is a normal subgroup of D8. However, when H was equal to the subgroup generated by S, then we found out that the left and right cosets are not equal when we take the element R. So they're not equal for all of G in G. So we have that H is not a normal subgroup of D8. And that is where the importance of having left cosets equaling right cosets. There are two helpful observations after the definition of a normal subgroup. The first one being, if you see that G is an abelian group, then automatically all of its subgroups are normal. And why is that? Well, think back to the example of the integers with H being 3z. We've said that because the addition is commutative, the group Z is abelian. So if we took 0 plus 3z, the left coset, and the right coset, it's going to be equal. And this is no matter if we took 3 or 4 or 5 or 6. So it could be any A, and it could be any G, and this would still hold because Z is abelian. So no matter what the coset is, the left and right will be equal, and so the subgroup would be a normal subgroup. So that's why all of the subgroups of G would be normal. The second observation is that sometimes it is easier not to work with this fact in proving that a subgroup is normal, but to do some algebraic manipulations. So H is a normal subgroup of G if and only if GH is equal to HG for all G in G. This is by definition. And if we perform G inverse on both sides, then by algebra we would get GH G inverse is equal to H for all G in G. Now, if you've seen the lesson about normalizer, centralizer, and center that I've put on the playlist, you would recognize this definition immediately. This is the definition of a normalizer. The normalizer of H, because H is the subgroup, the subset in question, and this normalizer, because it works for all G in G, then this normalizer is equal to the entirety of the group G. If you don't remember what a normalizer is, keep in mind, normalizer of a subset A is equal to all the elements G in G, such that GA G inverse is equal to A. So here we've said that this is true for all elements G in G. So instead of having it only this set, this is equal exactly to G. And A in this case would be H. In a sense, the normalizer of a subgroup H of G is a measure of how close H is to being normal. The maximum it can be is the entirety of G, but it could be a subset that is less than G. It's contained inside G. The more elements we have here, the closer H is to being a normal subgroup of G. A nice way to put all of this information together now is in this normal group characterization theorem. If G is a group and H a subgroup of G, then the 5 statements are all equivalent. That means if you prove one, you can prove all of the rest immediately. We will start by having that H is a normal subgroup of G. We will start over here in stating it. The reason I put it over here is because the proof of this theorem, which will not be done in this video, by the way, it will be done in the next video, will be done in this order. 1, 2, 3, 4, 5, and then 5 goes to 1. But, however, I will be explaining it in another order, just for it to make more sense. So, if H is a normal subgroup of G, we know by definition that the left and right cosets for all G in G are equal. So, 5 would give us that GH is a group. Okay, if GH is a group, we want to know what the operation is. The operation is given by if we multiply two elements of GH, which are two cosets, so GH times KH, that is defined to be giving the coset, which is GKH. So this is how we are defining it. We are basically taking the operation of G, which is being applied here on GK, and we are inducing the operation of GH by saying that, okay, if you want to multiply two cosets, you will multiply them by taking the multiplication of their representatives, G and K, and then giving us the new coset, GKH. And there we will, in the proof, we will also describe what the identity looks like and what the inverse of a coset looks like. The third equivalent statement is that H, the normal subgroup H, is the kernel of some epimorphism. I'd like you as an exercise to try and guess what that epimorphism is. So this is very nice because it allows us to essentially say that all normal subgroups are kernels of some epimorphisms. And we will find out in the future, probably in the next couple of videos, that all kernels are normal subgroups. So essentially giving a one-to-one correspondence between normal subgroups and kernels. So we can say in the end that any normal subgroup is a kernel and any kernel is a normal subgroup. And number 4, we have that H is closed under conjugates. So we've taken in general a subgroup is closed under the group operation and it's closed under the inverses. Now we're adding a third criteria for normal subgroups, which is closed under conjugates. A conjugate of H is GHG inverse. So this is closed. That means GHG inverse has to lie still inside the group H, the subgroup H, for all G in G and for all H in H. So this is what it means to be closed under conjugates. And usually this is the most direct way to prove that a subgroup is normal. It's just to check the conjugates and see they're all inside H. Number 5, of course, is that H is a normal subgroup of G. Therefore, finishing the statement of this theorem. Again, if you'd like to know the proof, it will be done in the next video, so stay tuned for that. Now that we have provided a complete characterization of normal subgroups, it is time to look at some examples. Immediately, we see that the alternating group AN is a normal subgroup of Sn, since we know it's a subgroup of Sn, and that AN is the kernel of some epimorphism. This time, the epimorphism is the sign homomorphism, where the sign takes a permutation in Sn and maps onto 1 and minus 1 with the multiplication. So this is an epimorphism, and evidently the group of even permutations AN is the kernel of this homomorphism. Therefore, immediately deducing that AN is a normal subgroup of Sn. And for the second example, we have immediately that the special linear group is a normal subgroup of the general linear group. This is because, again, with the same reasoning, SL and F is the kernel of some epimorphism, which in this case is the homomorphism, the determinant, where the determinant takes a matrix from GL and F and gives you a non-zero real number. So you can see how powerful this result is. Knowing that it's the kernel of some epimorphism is equivalent to knowing it's a normal subgroup. Lastly, we have that the subgroup generated by R is a normal subgroup of D to N. We've seen that in the case of D8, but we would like to generalize this. So how would we do that? Well, we were going to be listing the elements of D to N with a quotient of R. So this would be the quotient group of D to N with the subgroup generated by R. And the elements are simply, we're going to be taking the elements of D to N, and each of these elements we will multiply by the entirety of this subgroup, starting with the identity, and then R, and then R square, and then all the way to R to the n minus 1, and the elements S, SR, SR square, all the way to SR to the n minus 1. And as you said, each element is multiplied by the entire subgroup generated by R. Now that we've listed all the elements in this quotient, we would like to know if it's a group or not. If we prove that it's a group, then we can say that the subgroup generated by R is a normal subgroup because, remember, this is a normal subgroup if and only if this is a group. So let us see if this gives us a group or not. Notice that we can simplify this set here by seeing that the powers of R, when we're multiplying it by this set R, is just going to give us the same subgroup R back. So this is just going to give us R. All of these is going to give us this element here. Because when you multiply the powers of R by a power of R, you get back a power of R. So it makes sense to just write this for all of these elements. And for the other ones here, note that we can just multiply the R inside. So basically the subgroup generated by R will absorb these elements inside it. So we're going to have S times the subgroup generated by R. So these are the two types of cosets that we're going to have at the end of the day. So this set here, we want to know if it's a group or not. And the answer is yes, it is a group, and it's actually isomorphic to the group 1S. And this is equal to the subgroup generated by S. The reason these two are isomorphic is we can explicitly define the isomorphism phi taking from D to N slash R and giving us an element in 1S where you take the element which is either R or SR. So R is given to the identity, is sent to the identity, and SR is sent to S. So simple as that. That is the homomorphism defined. We can prove it's a homomorphism. We can prove that is an injection and a surjection, therefore an isomorphism. Therefore, since this is a group, the quotient group of D to N R, then this means that this has to be a normal subgroup of D to N. So far, we have encountered finite quotient groups. For example, we had the quotient group, which is R and SR. That is a finite one. And now we're going to encounter an infinite quotient group. So let us look at example 4 here. We have that the integers, a group under addition, is a normal subgroup of the real numbers. And the proof of that is going to be by proving that R, when we take the quotient of R by Z, we get a group. So when we take the quotient by Z, we need to essentially filter out integers. And we need to see what we will get when we go from a higher resolution, which is all the real numbers, into a lower resolution, filtering out by Z. So let us take an arbitrary element x in R, a real number. We have that the coset xz is given by when you take all of the integers and you add x to each integer. So for example, if x is 1 over 3, then you're going to have 1 over 3, and then you're going to have 4 over 3, and you're going to have minus 2 over 3, and so on. That's going to be your coset. Now graphically, if we represent the real numbers on this helix, we can see that the 1 over 3 coset, so 1 over 3 coset, it's going to be represented by these points. So 1 over 3 plus 1, 1 over 3 plus 0, 1 over 3 minus 1, and so on. Note that this is equal to 4 over 3z, which is equal to minus 2 over 3z. So again, it does not matter which representative we use, they all represent the same coset. Another coset could be 2 over 3. So if y is equal to 2 over 3. And then we would get the coset 2 over 3z, which is 2 over 3 plus 1, 2 over 3 plus 0, 2 over 3 plus 2, and so on. So now we've just stated two cosets. In fact, we have an infinite number of cosets, and all the cosets that we need are the ones where x is a number between 0 and 1. So x between 0 and 1. For each real number between 0 and 1, we get a different coset, a different line like this cutting through the helix. So the set of cosets here, it's between 0 and 1, but these are real numbers, and it's infinite, and it's uncountable because the real numbers between 0 and 1 is an uncountable set. So we have an infinite uncountable set in our quotient group. And the reason it's a group is because if you look here in the quotient group, we can say this is here is 0 and 0.1, 0.2, all the decimals until we reach 1 over here. So this is isomorphic to the unit circle because, of course, it gives us a circle. So our quotient with z is isomorphic to the unit circle, which we denote by S1. How would we describe the unit circle as a group? That's a good question. So the unit circle, first of all, as a set, is equal to e to the 2 pi I theta, where theta is a number between 0 and 1. So for each point theta, we get a point on the circle given by e to the 2 pi I theta. If you remember your Euler's formula, this is cosine of 2 pi theta plus I sine 2 pi theta. And if we graphically represent it on the real and complex plane, we get some point on the unit circle. So essentially saying that S1 contains all of the complex numbers which have a distance 1 from the origin. Distance is given by taking the norm of the element. This is called the norm. So first of all, we need to say it's a group, and that's why this is isomorphic to our quotient with z. So this means this is a group and z is a normal subgroup. So to prove that S1 is a group, we need to say that it is closed under the group operation. What is the group operation? Multiplication. Because if e to the 2 pi I theta 1 has a norm of 1, and e to the 2 pi I of theta 2 has also a norm of 1, then the product of these two elements would be using exponent laws, theta 1 plus theta 2. And that also has a norm of 1. So it is closed under multiplication. Moreover, multiplication, of course, is associative. That is a well-known fact. The identity of the group is when theta is equal to 0. So e to the 2 pi I times 0, which is equal to e to the 0, which is, of course, 1. The multiplicative identity. And lastly, the inverses. The inverse of e to the 2 pi I theta is e to the 2 pi I minus theta. Because if we take the product, e to the 2 pi I theta times e to the 2 pi I minus theta, we would get e to the 2 pi I theta minus theta, which is e to the 0, giving us the multiplicative identity. Therefore, S1 is a group isomorphic to the quotient R by Z, giving us that Z is a normal subgroup of R. And with this, we have finished today's lesson. If you've enjoyed, please like and subscribe. I will be giving many more lessons in the coming days. And please share with anyone who would be interested in the subject. I'll be seeing you the next time. Have a nice day and bye.